All right, let's talk about functional programming. I know it's a topic that's often surrounded by some pretty confusing jargon, but what if I told you it all just boils down to a few simple but really powerful patterns for handling data? Well, that's exactly what we're going to uncover today. You know that feeling, right? You hear terms like monad or functor thrown around, and you feel like you're on the outside of some secret club. It can definitely seem like a private language, but don't worry, we're decoding it all today. But here's the secret. You absolutely do not need a math degree to get this stuff. The password to the club is just recognizing a few fundamental patterns. And once you see them, they unlock a much cleaner, more powerful way to write code. So let's open the door. Okay, here's our game plan. We'll start with the core mindset. Gotta get our heads in the right space. Then we'll build up, starting with the simplest pattern, monoids, then moving on to functors, and finally, we'll tackle the big one, monads. Let's get started. So before we jump into any of those fancy-sounding patterns, we need to really get the foundational mindset of functional programming. And it all pretty much rests on two key pillars. The first pillar is the pure function. Think of it like a perfect, reliable machine. You put something in, you get a predictable result out every single time. A function like add x comma y is the perfect example. It only cares about x and y. It doesn't change anything else in the world. It just gives you their sum. Super simple, totally predictable, and incredibly easy to test. And the second pillar is immutability. Now, on the left, you see the way a lot of us learn to code. You just change data directly. The problem is that can cause all sorts of unexpected bugs somewhere else in your program. But on the right, that's the functional way. We never change the original data. Instead, we just create a new piece of data with the change we want. And believe me, this one simple rule prevents a huge category of really common bugs. So with that foundation set, let's look at our very first pattern. And it solves a problem that we as programmers face constantly, just combining things. I mean, we're always doing it, right? Adding numbers, sticking strings together, merging lists. So functional programming steps back and asks a really simple question. Is there a single, reliable pattern that works for all of these different kinds of combinations? The answer is yes, and it's called a monoid. I know, it sounds super academic, but it's really just a formal name for a pattern with two dead simple rules. First, you need an operation to combine two things, like a plus sign. And second, you need an identity element, basically a starting value that doesn't change anything, like 0 for addition or an empty list when you're joining lists. Look at joining lists in Python. It's a perfect monoid. The combining operation is the plus sign. And what's the identity element? An empty list, right? If you add an empty list to any other list, nothing changes. This simple, predictable pattern is absolutely everywhere once you start looking for it. Okay, so we've got a pattern for combining things. Solved. But what about a different problem? What if the value you want to work with is, wrapped up inside something else, like an item in a list, or maybe a value that might not even exist? The best way to think about this is with a little analogy. Just imagine your data structures, your lists, your optional values as boxes or containers. The value you actually care about is tucked away inside the box. So here's the challenge. Let's say you have a simple function, like one that just doubles a number. How do you apply that function to the number that's inside the box without all the hassle of taking it out, applying the function, and then putting it back into a new box? We want a standard way to just kind of reach inside and get the job done. And this is exactly where our second pattern, the functor, comes into play. A functor is just any box that gives you a standard way to apply a function to whatever's inside it. This is usually done with a method called map. You just give it your function, it applies it to the value inside, and then it returns a new box with a transformed value. Let's make this concrete. We could wrap a list like 1, 2, 3 in what we'll call a list functor. Then we can just call fmap on it with our function that doubles a number. The functor takes care of applying that function to every single item for us, giving us back a new list functor that contains 2, 4, 6. The best part? We never had to write a manual loop ourselves. And now, we've reached the peak of our climb, the infamous monad. We know how to map a simple function onto a value in a box. But what happens when the function you want to apply also returns a value in a box? This is where a simple functor kind of hits a wall. Imagine you map over a list, but the function you're using also returns a list. What do you get? A list of lists, a box inside a box. You get this nested box problem.
And that is usually not what we want. It's clunky, it's hard to work with. What we really want is to just end up with a single flat box holding our final value.
And this right here is the exact job of a monad. You can think of it like a superpowered functor. Its special operation, often called bind or flat map, does two things in one go. It applies your box returning function, and then it automatically flattens the nested result. It's like map and flatten combined into one single seamless step. The maybe monad is the classic example of why this is so amazing. It represents a value that could be something, or it could be none. When you chain operations using bind, if at any point a function returns none, the rest of the chain just gets skipped safely. This lets you write these beautiful, clean sequences of operations without a single if statement to check for nulls. It makes your code so much cleaner and safer. So we've climbed all the way from the basic mindset to monads, functors and monads. Let's just take a second and look at the view from the top and see what these patterns actually give us in our day-to-day coding. Well, these abstract ideas become incredibly concrete in stuff like stream processing. Imagine an infinite stream of data just flowing into your program. Using these patterns, you can build a really clean pipeline of transformations. Map this, combine that, filter this, and it just processes the data as it comes, super efficiently and without a bunch of messy state. So what's the big picture here? Don't think of these as scary academic terms. Just think of them as tools for your toolkit. When you need to combine things, reach for the monoid pattern. When you need to apply a simple function to something inside a container, use a functor. And when you need to chain operations that might fail or return another container, the monad is the perfect tool for the job. And that really brings us to the final thought. Now that you can recognize these patterns, the next step is to start seeing them out in the wild. So take a look at your own projects. Where do you have those messy loops, or those complex conditional checks, or just inconsistent ways of combining data? Which part of your code could be made cleaner, safer, and just more elegant with one of these patterns?